Hi. So we were seeing um, on the last video how to calculate linear functions, how to sketch a linear function by hand, and also how to plot its graphic using the GNU Octave environment. So as um, we are discussing, um, our goal right here is to build an intuition of functions, since these such functions are used to we can use it when we start our discussion more deeply and more specific about signal processing. And as I said, as I've been said, this throughout these videos, this is a different way to approach signal processing, and I'm using the literature. The book that I'm using is the Calculus One from Hamilton Luis Guidaresi. So you can tell why we are approaching signal processing this way. We are starting, um, we can say from the beginning, we are approaching from the calculus door. But again, this is a unusual way to approach signal processing. Yes, my goal right here is to approach signal processing, but this is not the usual way. If you search for signal processing courses online, we will find very nice courses, and they start approaching like the sine function, trigonometric functions, and how to discretize such functions, and also signal processing theory, which is a specific math. And okay, so as we already saw the basic functions that we'll learn on your high school, we saw square functions, cube functions, inverse functions, square roots. We saw uh, continuous functions, linear functions, also conditional functions, and also we are trying to adapt such functions, such problems to real world problems, and I'm giving emphasis in financial problems because this is a nice way to use signal processing. Of course, we got other problems on the real world that we can use signal processing, like physical signals from sound, from uh, equipment, uh, instrument equipment, and we are we are doing this all intuitively as we um, pass through the lessons from the book. Okay, and finally we start to approach trigonometric functions. Okay, so this is the topic of this video. Trigonometric functions. And of course, we are talking about sine and cosine functions. Okay, the only way that we can approach such a topic is with calculus theory. So we cannot get away from this. And let's start with this theorem. And this theorem that we will see solves completely all problems referent to these functions. So exists a unique pair of defined functions in the R set indicated by sine and cosine. Which satisfy which satisfy the following properties. So first property, sine of 0. And these properties you might already be familiar with because we saw with very often, even in the most ingenious calculus. The second, cosine of 0, which is equal 1. The third, for any real number A and B so sine of A minus B is equal sine of A, and now we'll put this in parentheses, cosine times cosine of B. Now we can just left outside, times cosine of B minus sine of B times cosine of B. And the fourth property of this theorem that solves completely all problems um, related to these functions for any real number a and b. Now cosine of a minus b is equal cosine of a times sine of b, now plus sine of a times sine of b. And the fifth one, and the last, says that exists or greater than 0 in which we got this interval. So sine is between 0, sine of x is in between 0 and x, which is in between sine of x and tangent of x times tangent of x which is equal or odd no relation between sine and cosine. This one we know very well. So sine divided by cosine. And this for x on the interval 0 and r. Okay, so before we start to discuss about, well, we are already discussing about trigonometric functions, but what we want right here is a visually discussion. We wanted to discuss about the signal and its properties and how we can sketch such signal, how we can work with the signal not only on the as a function of x, but we can adapt this as a function of time, and how we can plot such a signal using the octave. So first we need to know these properties. Well, some of these properties we know very well, like sine of 0, cosine of 0. Actually, all these properties we know from trigonometric or studies in trigonometric, and we still got some more to cover. So let's continue. So from the theorem, doing it. And for A equal B equal T, we obtain cosine of 0. So let me just bring the fourth property, this one. Okay. And now if we do cosine of 0, we will be obtain, and doing A equal B equal T, cosine of T times, let me see, right here, sorry, right here is cosine. So correct this, it's cosine of A times cosine of B on the fourth property of this theorem. So sorry, and correct this please. It's cosine of B. So cosine of T times cosine of T, because we are doing A equal B equal T, plus sine of T times sine of T, because A we are doing as equal T, and cosine of 0 we know that is 1, and now cosine square of T plus sine square of T. So this is the trigonometric identity that we know very well as well. And this is the property number 6. Okay, and right here, forgive me about this, is cosine of A times cosine of B. So cosine of A minus B is equal cosine of A times cosine of B plus sine of A times sine of B. Okay. So this way, for odd t, the point cosine of t, sine of t, it lies on the circumference. So it lies on the circumference x squared plus y squared equal 1. And we can do this representation with the trigonometric circle. of radius 1. So its radius is equal 1. So 1 minus 1 minus 1 and 1. And this is the axis x, the axis y. And for example, if you wanted to do where is the point P, we can decompose your position in terms of sine and cosine. So right here we got sine of t, and right here is cosine of t. Okay. And we can see right here is sine, and right here is for our cosine. So I got one more thing to represent right here on this trigonometric circle. We got this A. So we wanted to know, we can know not only the localization of this point P on this circle, but also this works for this arc. So we wanted to know the measure of this arc. So a arc AP we can measure this way in a radians. And we got one more. I said that from the theorem. So from the theorem, we got 5 properties, and from these properties, we abstract these other properties, as we are seeing. And we got a property of number 7, and let me see, I think now this is the last property. So number 7, and says that exists a smaller number a positive smaller number. So exists a positive smaller number a such that cosine of A, it's equals 0. And for this A, sine of A is equal 1. And this positive and smaller number, so this number can be used to define P. To define the number P. Okay. So definition. We define the number P by P equal to times A, where A is the number that refers to which is best, which refers to the property number 7. Okay, and with that being said, we can say that, for example, this way, pi over 2, I'm saying p, sorry, it's pi over 2 is the smaller number positive smaller number. Such that cosine of pi over 2 is equal 0. And we also have sine of pi over 2 which is equal 1, as this property is showing to us for a positive number a. So let f be a function defined defined in a set R, in a R set, we say that f is a even function if for all x f of minus x is equal f of x, and for all x in a set of R, this is satisfies this function. We say that this function is even. By the other hand, on the other hand, on the other hand, that f is an odd function, if for all x f of minus x is equal to f of minus x if the function is odd. Okay, so this is all the theory, and as you can see, is very short. We can learn it this with just 30 minutes, less than 1 hour, and because it's very simple, and with trigonometric demonstrations, um, which is better to learn when we are doing this visually, not just doing calculus, also sketching um, the arcs on the trigonometric circle. Sorry, I said trigonometric functions. Okay, so we have to, it's best to learn if we do this visually sketching um, arcs on the trigonometric circle. And of course, it's also good if we do, if we solve some examples, some exercise, just to know um, how this is works. And this is what actually we are about to do right now. We will just solve some examples, And then I think we are ready to start to scratch these functions. And of course, we will do this also in the octave. And trigonometric functions is like the beginning, the open door for signal processing. And as I said, and I will say that again, on the real world, and as we already saw on the last video, when we sketch the linear function and we use a example, we import uh, we import data into the octave and we ask to Octave to plot this data, and you see that we obtain a graphical which with um, a number of linear um, a bunch of signals, and I said that these signals we can, if we do a adaptation, a analogy with linear function, we can say that is a collection, is a sum of linear functions, and trigonometric functions, sine and cosine functions uh, is one of the main signals that we work when we are discussing about signal processing. And okay, the data that we plot on videos way before, I said that on the real world signals are not always well behaved, and we need to be able to recognize such signals, and we can have a signal which is a mix of different type of functions. So we can have a signal with a square function uh, and a linear function. And also, what is important to know, to let clear, is that we got a variety of signals, a bunch of signals. We do not have 1, 2, 10, 12, 50. We got infinite type of signals. Okay, so we are just trying to understand how these signals can show up, and yeah, that's it. So let me just solve with you this first example, and again we are using uh, the Hamilton-Lewis Guideritzing book from Calculus 1. So this is not something that I'm making up. I'm using the book. Um, when we start to try to adapt these problems to financial or other type of problem, maybe on this moment I will start to making up problems, because this is also our goal right here, which is use this theory to solve real world problems. Okay, so let's solve this example, and let me also indicate the number of the example. So is the example number 1. Okay, so show that a sine is a odd function. So doing in 3. So let's got 3 right here. So doing in 3 that A is equal 0 and B is equal T. So sine of 0 minus T, which is equal sine of 0 times cosine of T minus sine of T times cosine of 0. Cosine of 0 is 0, so this term will be totally cancelled by 0, and right here we got sine of minus T and cosine of 0, sorry, is equal 1. So yes, is an odd function. So sine is an odd function. A odd function. So yes, okay, we got the letter B also. So the letter B asks to us to show that cosine is a even function, is an even function. And doing in 4. So let's bring this property. Again, that a positive number equals 0 and B equal T. So we will be taking something like 0 minus t oh, forgive me this nonsense, minus t only. I don't know why I look at this minus t right here. Okay, so 0 minus t and cosine of 0 times cosine of t plus sine of 0 times sine of b. And again, sine of 0 is 0, so all this term is concealed, is 0, is concealed. And cosine of 0 is equal 1, so this term will become cosine of t. And this is cosine of minus t. And this is not a odd function. To be a odd function, it must to the function it must to assume this shape, just like right here, f of minus x, which is equal f of minus x, and right here we are obtaining cosine of minus t, which is equal cosine of t. So right here is not a odd function, an odd function. Okay, let's see this another example. We are just working trivial examples, basic examples, and you see that it's not so hard as it looks like. So example number 3, show that for all x actually let me do this different. Yeah, this is the statement of the problem, but let's say if I ask to you to calculate cosine of 2x, and we know that this is basically the same as cosine of x plus x, right? And now let's use the properties that we have just learned to solve this. So let's see the property number 4. Okay. So if we say that rewriting this cosine of 2x as cosine of x plus x, so uh, this means that a is equal x and b is also x, so a is equal b, so a is equal b, which is equal x. So right here, cosine of x times cosine of x, and right here, sine of x times sine of x, having this set. Okay, and this is equal cosine square of x, and this is equal sine square of x. So cosine of 2x is equal cosine square of x plus sine square of x. Okay, and also ask to us to show that for all x, it already gives the solution of sine of 2x, and let's do different. Let's say is asking to us to calculate sine of 2 2x. Okay, and let's bring the properties related to sine, and if you can notice, this is a sum of arcs, and right here the property of number 3. Okay, and again, this is the same as we write as sine of x plus x, so this is a sum of arcs, so this is sine of x times cosine of x minus sine of x times cosine of x. And actually, right here I commit a mistake because of this signal right here, and because of the property, we will be obtain right here a negative signal, and right here because of this is minus, and on the property right here is minus, the signal will change, and this is equal to sine of x times cosine of x, because these terms, if you can notice, they are repeating. Sine of x times cosine of x and sine of x times cosine of x. These terms are equal, so we have just to sum up them. And so sine of 2x is equal to sine of x times cosine of x. Okay, so let's solve one more example. Now the example 4. And again, ask to us to show that for all x, and it passed to us a trigonometric function with its solution, but let's do different. Let's say that it's asking to us to calculate this trigonometric function. So now we wanted to find the cosine square of x, knowing uh, all these properties that we already have saw. So first property, and let me say what number is this property. I think is the number 6. Yeah, property number 6, which is the trigonometric identity. So this is the first property that we will bring. So we know that cosine square of x plus sine square of x is equal 1. And from here we can, well, first let's do something right here. We saw right here that cosine of 2x is equal cosine square of x minus sine square of x. So base it on this property. Actually, I think now is best if we follow the statement of the book. So it gives to us and asks to us to show that for all x, cosine square of x is equal 1/2 plus 1/2 of cosine of 2x. Okay, so we need to show that for all x, cosine square of x is equal this value. 1/2 plus 1/2 cosine of 2x. 1/2 plus 1/2 times cosine of 2x. Okay, so we got these properties, and let's work first with this one. So cosine of 2x, because this way we can isolate this second part of the solution. Okay, from here, let's isolate um, sine square of x. So from here, we can say that sine square of x is equal 1 minus cosine square of x. So cosine of 2x is equal cosine square of x minus 1 minus cosine of x. And now rewriting this and doing a distributive on the signal. So cosine square of x minus 1 plus cosine square of x, and this is equal to cosine square of x minus 1. Okay, right here we are just doing algebraically manipulations, and we can go on writing that cosine of 2x is equal to cosine square of x minus 1. And remember that it asked us to prove that cosine square of x is equal to this, and from here we can isolate. Let's just switch the sides of the equation, the side of the terms on the equation. If we switch sides, we will write this way. And now if we want to isolate cosine square of x, we just need to sum up ones on both sides. So cosine of 2x plus 1, and now dividing both sides by 2, and right here is 2, and we will obtain cosine square of x equal 1 over 2, or 1/2, plus cosine square of, cosine of 2x. First, let me write this as a constant, 1 over 2 times cosine of 2x. Okay. This is just a exercise that we do to know how to do this type of algebraically manipulation with cosine and sines. We can do this for sine square of x, but right here this is not necessarily. It's not necessary, and let's move on with the content of this topic, and we almost getting in the representation of the signs, the signals, sorry. Okay, and we will do this on this example. Example 5. And ask to us to calculate a cosine of pi over 4, b cosine of pi b is sine of pi over 4, and c, which is equal cosine of pi, and d sine of pi. Okay, so as you can see, we are just starting to work with signals, and as I already said to you, these signals with these functions cosine and sine, they are the most commonly shown in signal processing, and further we will see that and this is already signal processing theory, that if we add successive cosines and sine into one signal sign, we can represent all types of signals, a variety of signals, just by summing up these signals, cosine and sine, into one signal, into a single one. For a, we can use this relationship and right here what we would do is to plug in a real number x equal pi over 4. I said real, but let's see, is a positive number. So a positive number. So let's apply x as a positive number. So doing it, x equal pi over 4, and using this relationship, so cosine square of pi over 4 is equal 1 over 2 plus 1 over 2 times cosine of 2 times pi over 4. And doing this, we will be obtaining pi over 2. Okay, so it's 2 times pi over 4, and we will be taking 1 over 2. Okay, so right here is cosine of pi over 4. Okay. If you can notice, right here we will be taking cosine of pi over 4, which is what we wanted to calculate. And right here is cosine square of pi over 4. And if we now subtract cosine square of pi over 4 of both sides, so if we cut right here and if we cut right here, we will be taking cosine pi over 4 I think we cannot do this actually. We still got this constant 1 over 2. Right here I do this and I'm still commit this mistake. Right here, of course, is 1 over 2. So pi over 2. And now I can multiply this. So cosine square of 1 over 4, which is equal 1 over 2 plus cosine pi over 4. And I don't know, I'm just doing this intuitively. It look right for me. Maybe I'm wrong. And if it's the case, please let me know in the comment. Oh, okay. Now, okay. And now this I'm taking from the book. It says that as cosine of pi over 4 is greater than 0, but right here, what I will do is, well, we got 1 over 2, but we can do, the problem right here is, right here, to obtain this solution and with only one, with cosine of pi over 4 instead of cosine square of pi over 4, I should multiply for cosine of, I don't know, minus 1 pi over 4, and or yeah, in this way I could conceal this term on this side, but doing this, I will multiply this term also, you know. So at this moment, let's just ignore what I did right here because, as I explained, uh, this term affects the answer, the final result, because I could multiply this side by cosine over with this exponential minus 1 in this side too, but this way I have to multiply by this term also. And now I'm just getting the answer of the book, and cosine of pi over 4 is equal the square root of 2 over 2. Let me do a quick research right here. Okay, I did a quick research, and well, this is why it's important to know this, what we call as notable angles. So let me sketch this because we will use from now. So notable angles. So it's very important to know this, and from my research, cosine of pi over 2 is equal 0. So doing this, we will obtain this solution perfect. And this is the same as cosine of pi over 4, which is equal square root of 2 over 2. Okay, so now let me pass to you these notable angles. And again, that is something that you probably might have seen in your high school days. So we got the sine, and the notable angles, they are 30, 45, and 6. And you might be familiar with this table. So sine of 1 over 2, which corresponds to this notable angle, and sine of 1 over 2 is a notable angle, 45, 60, square roots of 2 over 2, square root of 3 over 2, and cosine square root of 3, over 2, square root of 2 over 2, and 1 over 2. And we got also tangent, but I will let this out at this first moment. And actually, this list goes on. We still get as a notable angle 90s, 180, 270, and 360. And now let's get the trigonometric circle. So right here's for cosine and right here's for sine. And if you notice, right here is on the top right here is pi over, let me bring this a little bit down. Right here is pi over 2, which is equal 90. And if you can notice, we do not have a component for this angle. So cosine of pi over 2 or 90 is equal 0 because we do not have a component for this angle. If we try to decompose, let's say, it for the angle theta of this vector right here, we can decompose for this theta at any part right here on this angle a component, but right here we do not have a component for cosine. And because of this, we know that sine of pi over 2 or sine of 9 is equal 1 because right here the component is right above of the sine, this axis. Okay, so we just have calculated cosine of pi over 4. We know that is right now, which is same as square root of 2 over 2, which correspond to a notable angle 45. And sketching this is about right here 1/4 of this trigonometric circle, pi over 4. Okay, now let's try to see what we can do using the octave. Let's plot a cosine function on the octave. Okay, now we are here on the octave, and first a resource very nice from octave, it's the documentation. We on right here we can do searches. Let's search for cosine, the cosine function, just cos. Let's see what you can find. right here. Maybe we can plot directly without any complicated um, code. So let's do something like a cosine of x and ask to plot x and y. Let's see what it returned to us. Run? Nothing. Now let's build a vector or use the function line space. So x line space and pass the limits in the number of points. This is will create a array of x. Nothing. And I suggest to you, I strongly recommend to you to do researches on the document because right here Octave offers a bunch of code that you can use to learn, to do experiments. And we can probably find some piece of code right here that we can use. Of course, we are working with a trigonometric function. So not only, but I think, okay, not only we need to consider um, cosine of x, but we need to consider the pi number. But I almost sure that Octave offers something that we can use. Cosine. Okay, let's do by ourselves, and on the next video, as we are starting to work with these functions, uh, Octave is perfect for this type of functions and offers a lot of resources that we can use it. So again, instead of facing this as a function of x, let's face now as a function of time because signals it got the time base. So now I even do comments let's say we are interested in a continuous signal, continuous signal, and now let's create a vector which starts from 0 and the step is 0.01 and it ends at 2 times pi. So this is our time base. And now the x function, which is, we can say this is y, which is equal cosine of t instead of x. Um, let's see something because we were doing this, and now let's say that again creating a vector, the step and now 2 times pi. Let's see now. Now it works. it works very nice. Um, so that's it. We have done it. Okay, let me see now if I do this over 4. Okay, it works. Let me take a print of this. And this is the 45 angle. Okay. So maybe you you might saw animations that the signal is varying this way. So this is a in electrical signals. This is called phasor. So this phasor is going up and down, and as it is going up and down, is varying the signal this way. So it's something this way. Okay, I'm trying my best. um, okay, and again, instead of facing this as a function of x, we face as a function of time because this is a time base, and this is the same. Of course, right here is t. It's the time base. Okay, so there it is. Let's change the. Let me see the limits of the axis is 1 and 2. Let's switch. Let's just plot this way. And we got the cosine function. And cosine of pi over 4. Let's try do. Let me see. Now let's ask to plot pi over 4 cosine of pi over 4. Let's see. Let me close. If we add hold on, so we can plot both of these lines, and now right here probably is the angle of 45 degrees. I have to study this better. Let's try if I do something like T2, and now right here pi over 4, and also asked to plot T2 y in a different line width. I let this way. Let's see what happens. And again, hold on. So just for to show you, we can do right here. Hold on. I hope so. Let's see what happens. Let me put this right here. And I think it's best if I try to change the color, or at least the line width. Or should I do a different with the same time base in a different, not only the time base, but also let's change we don't need to change the function, just the time base. Okay, and let's use a different line width. So right here, a line width of 2. Let's see what happens. It doesn't work it. Okay. Um, this video I think is very long right now, and this is all for now. Hope you like it. Hope you enjoy. Um, we will do more of this on the next videos, and that's it. Thank you.